Hello Year 12, this is video 1B. Okay, question 5 we didn't get to last time. So you could try this yourself, but it does have a little bit of a trick to it that you may or may not be familiar with. So find B and C if this equation solves, if this function solves y dash equals 3y minus 18x. So we need a y dash, so let's find that. So y dash equals 3e to the 3x plus b. That's it. So what do we have? Let's look at this. So we're y dash, so 3e to the 3x plus b equals 3y, so 3, lots of e to the 3x plus b, x plus c, minus 18x. Now, we can see there's the same thing there, both sides, but let's maybe just expand. So 3e to the 3x plus b equals 3e to the 3x plus 3bx plus 3c minus 18x. And they cancel. And I'm going to put everything on one side. 0 equals. Now note here that we've got x values and we've got constants, and it's really important I'm going to put them together. So the x values first. So we've got 3b minus 18 lots of x plus, and then 3c minus b. Now what we have here is not really an equation but an identity. It's saying that for all values of x, this expression on the right-hand side has to equal 0. There's a special symbol for that. That's identically equal to, all right? And what that means is that the coefficient of x has to be 0, because the coefficient of x on the left-hand side is 0, so the coefficient of x on the right-hand side equals 0. So if we're going to equate coefficients of x and the constants. So we get 3b minus 18 equals 0, which very quickly gives us b equals 6. And we get 3c minus b equals 0, which quickly gives us c equals 2. Okay, the question was find b and c. We found b and c. Okay, so it's really just an algebraic exercise, but it relates to differential equations. Okay, up to 6b now. So show that, this is another verification, but then there's finding some particular solutions, and I'll show you some nice graphics to do with this as well. Show that y equals a e to the x minus 1 is a solution for this differential equation for all values of a. All right, so, well, we've got a y dash, so that's what, so y dash equals a e to the x minus 1. And so now we'll sub into y dash equals x plus y. So the left, not sub really, but the left-hand side is y dash, which is a e to the x minus 1. And the right-hand side is x plus y. So that's x plus, and then what's y? You can see how this works. The x's will cancel. A e to the x minus 1. Okay, and so that the x's do cancel. Oops. A e to the x minus 1, which is the left-hand side. All right. Now, so we've shown that. So now, what about this part here? Find the particular solutions given these points. So we're finding, really, we're just finding the values of a. Just like in other cases, we'd be finding the value of c. Right, I'm going to just sort of shrink that a bit so doesn't get in my way. All right, so what am I starting with? I'm starting with, just continuing B over here, y equals a e to the x minus 1. And when I put 0, 0 in, then I've got 0 equals a e to the 0 minus 0 minus 1. And a e to the 0 is a. All right, so 0 equals a minus 1. And so a equals 1. And the particular solution is y equals e to the x minus 1. All right, a e to the x where, all right, there's a 1 there. All right. Okay, now what's next? 0, negative 2. So y is next, so that's negative 2 equals a e to the 0 minus 1. So negative 2 is a minus 1. A is negative 1. And so what do we get here? We get, when a is negative 1, y equals negative e to the x minus 1. You can see here that these things are not just differing by a constant, all right? And finally, 0, negative 1, we actually end up with a equals 0, just to cut this short a little bit, and so therefore y equals negative x minus 1 in this case. So the differential equation y dash equals x plus y, if the function is known to go through 0, negative 1, then there's no exponential term in it at all. All right, so I just feel a little bit fancy here. So this point goes with that. Let's see, this point here goes with that, and this one goes with that. And I want to show you this in GeoGebra. It will make you go, wow. But first of all, we've got a little aside here. Where do we have y dash equals 0? Now, think about it. If I ask you, where does y dash equal 0, what do you do? Oh, I've got to differentiate and blah, blah, blah. No, the information we have here is that y dash equals x plus y. And so if we're given, or we're seeking, really, seeking y dash equals 0, then that means that x plus y equals 0, or y equals negative x. Okay, so keep that in mind for when we have a look at the at GeoGebra as well. Okay, I'm here in GeoGebra. I've prepared these things earlier because it takes a bit of time to do. So I've got 3 points plotted, A, B, and C, which are in order, the 3 points that we looked at. Okay, 0, 0, 0, negative 2, and 0, negative 1. And I can plot the 3 functions that we found. Okay, so you can see their equations on the screen there. Those are the 3 equations that we found, and they do indeed go through the points indicated. But do they solve the differential equation? Well, it turns out, you haven't learnt this yet, but this is part of the topic and just want to give you a feel for it. There's something called a slope field that gives us a visual indication of the solution of a differential equation. And here we go. This slope field gives us it shows you no matter where you are on the number plane, it gives you an indication of the gradient of the potential function at that point. So it really is kind of showing you a family of functions. A differential equation has a solution that is a family of functions. And I just hope that you can get a little intuitive sense of the relationship between all those crazy little lines and the 3 things that we have here. if I plot, if I'll get rid of these three, what I have plotted here is a constant. I couldn't call it a because that's the name of a point. So I called it k e to the x minus 1. That is our general solution to this differential equation. And if I manipulate the constant at the front, then I get all of these different equations, right? And yeah, it's kind of like iron filings all over the place being pushed in a certain direction by a magnetic force. And the function that I've plotted is just charting a course through those filings, obeying the signals as it goes. Okay? Now, one more interesting thing, and I reiterate, this is not a family of functions that just differ by a constant. They look very different indeed, especially that versus that. Now, one more interesting thing. In the aside, we asked, where do we have y dash equals 0? And the answer was where y equals negative x. Well, I can graph y equals negative x. There we go. And so normally when we ask where does y dash equals 0, then we say, oh, it's when x equals 7. Or it's at 7 comma negative 3. We give a point or a few points where there's a stationary point. But here we have a family of functions, not just one function with one stationary point. We have a family of functions with a family of stationary points. And if I be brave and try to put a point at the intersection of those, there we go. What you can see is where this curve has a stationary point always occurs simultaneously with y equaling negative x. It occurs on that line. Isn't that interesting? And then in these ones, well, it doesn't go through the y equals negative x at all, and that agrees with the fact that the function does not have a stationary point. There's our straight line. Okay? So there's more we can say about slope fields in the future, but I just want to let you know that they are part of this topic. They're highly visual, and in an introductory lesson on differential equations, well, it's good to see what we mean by a family of functions, really. Okay, back to, right. Section 7, different types, the types of differential equation in this topic. We've seen these. dy dx is a function of x, you just find the primitive. The next ones, dy dx is a function of y. You can't just find the primitive there. That's the topic of lesson 2. Third ones, dy dx is a function of x times a function of y. That is the topic of lesson 3. Now, that is a drop in the ocean of differential equations, of different types of differential equations, but those are the 3 types that we specifically learn how to solve. This one here, we know that's exponential growth, and this is related to exponential growth because there's the exponential growth part and there's a different part. And I'll just quickly say, we will learn this in detail later in the topic. This is called logistic growth. And it's a more realistic version of exponential growth. If you use exponential growth to model a population growth, well, first of all, the negative values for time, if time and population, negative values mean nothing. So, well, you get something that goes towards infinity in an insane way. And if we were talking about the population of Australia growing by 5% per annum, for instance, well then, let's say, sorry, the diagram's getting messy, but let's say this is where we are now, 25 million roughly. Then what's this predicting? Well, in 100 years, that the population of Australia will be, 3 billion or something like that. It's simply not reasonable. It's not a realistic model as time goes on. So logistic growth it puts a cap, right? Puts a maximum, say maximum population, and you get a curve like this. That's very badly drawn, but the point is it looks like exponential to begin with, but then it goes away from the exponential, and this is very, very deeply related to the pandemic that we're in at the moment, because we had exponential, what looked like exponential growth in COVID-19 cases, but that can't go on forever, and we have a maximum number of people who can be infected, that is the whole population. Something interesting here, there's an inflection point there, right? And the inflection point, now, when you hit the inflection point, then you are halfway to the maximum. Now put yourself back in, a few weeks ago, and we had this situation where we felt like it was going up exponentially. What everyone who was modelling it was looking for was, where's the inflection point? You don't know when it's going to be. The inflection point is when the rate of cases slows down. So the most important item of the evening news was how many cases were discovered today. When that number starts going down, then it means you're past the inflection point, and it means you can now have some guess as to what the maximum number of infections is going to be, at least according to the model, but it allows you to do some planning. Okay, moving right along. Section 8. So differential equations can be first order, second order, third order, and so on. I've covered the idea of that. So basically a first order, could be something as simple as that, or that, or that, or y dash equals 7y. Okay, the fact that we've got y here instead of x doesn't change anything. It's still a first order differential equation. And it could be something, y dash squared minus 3y plus x equals 0. We're not going anywhere near something like that, but that would be a first order differential equation. Second order is the same, but can involve the second derivative. So x squared y double dash plus 3y dash minus 7y equals 15. That would be a second order differential equation. We're not going anywhere near that. Third order, well, if I just, put in a third derivative there, then now that's third order as well. Our course includes first order differential equations of particular types and simple second order differential equations. An example of that would be if I asked you to solve y double dash equals 3, then you can very quickly get y dash equals 3x plus c, and then y equals 3 on 2 x squared plus cx plus d. So it's got two constants in it, and you need some information about a y value and a y dash value if you're going to work out what those constants are. So I think that's fair game. That's a very simple second order differential equation. All you need to do is integrate twice. All right, so differential equations can be linear or non-linear. And the syllabus says that students need to know the features of a linear first order differential equation. Maths in Focus doesn't really discuss it, Cambridge does. And I think that Cambridge does the right thing because it's letting you know what the features of it are. It could obviously be a multiple choice question. Which of the following is not a linear first order differential equation? So this is it. It looks quite technical, which is why I left it to the end, or to near the end of the video. But what we have is we have y dash and y. And neither of them are squared or in the bottom of a fraction or anything like that. So it's first order, and linear means that there are no powers attached to these things. Now taking for granted the y dash and y, let's now have a look at what else we've got. We can have a function of x attached to the y, and we can have a function over here, also of x. Okay, this is a linear first-order differential equation. Now, the following equations are in the given form. So y dash equals 5x cubed. So this could be written as y dash plus 0 times y equals 5x cubed, right? And so you've got that colour and that colour, right? It matches the definition. Right. Oops. Right, the next one. Y dash minus 6y, that's already in the right form. So y dash, we've got the negative 6 is f of x, and 0 is the g of x. And now we've got y dash minus 4xy, so that's a genuine function of x, and 3x squared. All right. Now, these are, why do these have to have a name? Well, I can't say from experience, but I'm gathering that there are techniques for solving any linear first-order differential equation. And so if you're going to use the same techniques for solving them, then they need a name. Okay, the next ones. These can be written in the given form. So think of a question that could say, show that one of these questions is a linear first-order differential equation. Well, you would rewrite it in this form, right? So x squared y dash plus xy equals 0. So what's the problem with this? The problem is that in the given form, there's nothing attached to y dash. So we're going to divide by x squared. And that will give us y dash plus 1 on x times y equals 0. 0 divided by x squared is 0. I've written this as 1 on x times y to emphasize the function of x there. Right? Okay, so that's in the given form. If it was a show that question, you might continue, equals y dash plus f of x y, sorry, not equals, silly me, equals g of x, where f of x equals 1 on x and g of x equals 0. That's showing that you know how to answer the question. Show that it's in show that it's a linear first-order differential equation. Well, you're showing that it's in that form. All right, so that can go. Now, this one. What's the problem with this one? Y minus e to the x. Well, I'm going to write it in the right order first. So e to the x y dash minus y equals negative 1. So multiply through by negative 1. And we need to divide by e to the x. So y dash minus e to the negative x times y equals negative e to the negative x. Okay, so that's in the correct form. I should say that you've got to be careful when, like if you divide by x squared, you could be dividing by 0. That's definitely not something we're going to think about here unless explicitly told to. Okay, and now divide through this one by sine x, so you get y dash minus cos over sine is cot, so cot x times y equals, and 1 over sine x is cosec x. All right, so just play with my highlighter again. There we go. All right, so that should be nice and clear. All right, classify the following. Y dash equals y over x. So let's just go y dash times x equals y. Does this look like a linear one? So, well, I don't really like it like that actually, but I'll say y dash times x minus y equals 0, and now divide through by x. So y dash minus 1 on x times y equals 0. So this is linear. And B. Clearly this one will be non-linear because you've got to have one of each, haven't you? So if you multiply through by y, then you get y dash times y equals x. And I'll just write it like y times y dash minus x equals 0. But I can't have the y here, but dividing by y gives us a big problem. Y dash minus x over y equals 0. That's a correct statement, but it's not a linear first order differential equation because this is not something multiplied by y. Okay, this is a big problem. It's x times 1 over y, it's not x times y, and there's nothing we can do to put y on top, to bring it out. Okay, so that's that. And finally, I'm trying to make this really quick, some interesting and important differential equations, just for interest. If you stop the video now, you're not missing out on being able to answer any questions, but I hope you have an interest in how mathematics is applied outside the classroom. So the first one is projectile motion, or it's throwing an object in the air, right? When you throw an object in the air, then y is the height of the object. You'll learn all about this term. Y is the height of the object, and g is gravity, the acceleration due to gravity. We're about 10 meters per second. And that's the only thing this is the only equation needed. If you throw the object straight up and it comes straight down, this is the only equation needed to describe what's happening. You're simply saying that the acceleration of the object is negative, that's towards the ground, g. And from that you can derive the velocity and derive the displacement. So you can end up with y equals negative half gt squared plus ct plus d, and this will be the velocity, and this is where you started throwing it from. Okay, so the point is scientists observe that this is what's changing in the situation, and then they derive everything else. All right, just very quickly, this one is oscillation. So like a pendulum, okay, swinging backwards and forwards, and basically what it's saying is that the acceleration, I'll talk about a spring instead, right? If you have a spring and then it goes, you let it go and it goes boing, 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 then here's your equilibrium point. This is like positive x, this is negative x, and so when x is positive, when the position of whatever's on the spring is positive, the acceleration is towards the middle, it's negative. And when x is negative, the acceleration towards the middle is positive acceleration. That's exactly what's being said here. K is just a constant. All right? And once again, from that, you can derive all the other equations of motion. All right, this one is variable gravity. If you go to the top of Mount Everest, then gravity is weaker than it is where you are. And for instance, water will boil at a lower temperature. And so if you drop a heavy object from 10 kilometers above the Earth's surface and want to calculate how long it takes to get to the ground, you have to take into account the fact that gravity is not the same all the way through. This is the differential equation that gets you started on that. All right, this is exponential growth. This is cooling. All right, so get an object out of the oven. We've done this before, 25 degrees, and it works its way towards that in an exponential fashion. Right, it all starts with this differential equation. This one is the logistic growth. So if the maximum of population was going to be, say, 560 million in some big country, then different values of k, you get different curves and so on. So you need some data on how the population's actually growing to get your value of k, and then you can make predictions about the future. This one, I just looked it up on YouTube. It's about a rocket and thrust. Okay, so interesting thing about rockets. Does that look like a rocket? Looks like a house, doesn't it? Does it look like a rocket now? Right, so the rocket goes in that direction because it's burning fuel to generate thrust. As it does that, the rocket's getting lighter, which means it'll go even faster. So it's quite a complicated relationship between the mass of the rocket and what it's doing. So I won't say any more, but this is the differential equation that describes the motion of a rocket under its own thrust. And finally, this is to do with diseases, the spread of infectious diseases. It's called the SIR model. You can look at a YouTube video if you want to see more. It's really fascinating. Very much being used at the moment, of course. 3 differential equations. S for the population that is susceptible to the disease, i.e. they haven't had it yet, so they could catch it. I for the part of the population that's currently infectious, and so they can infect other people. And R for recovered. People who have gotten better, they won't get the disease again. And so, And so S plus I plus R equals the number of people in the community. But over time, the balance of these changes. And you've seen, of course, we've all seen graphs about, flattening the curve and so on. Well, just very quickly, this is saying that the susceptible people, they will change over time because susceptible people will interact with infectious people and some percentage of them will become sick. The number of infected people will change over time for exactly the same reason. Some people will become sick, so that means that more of them, that's a positive, but then we subtract the percentage of people, the percentage of infected people who get better. So gamma is a constant describing, the rate at which infected people get better. And then the recovery part, well, that's just this bit moved down here and made positive, right? People who were infected, a certain percentage of them at any time get better, and that means that the recovered part grows. All this is described in here with lovely graphs. Okay, so that is the end of lesson 1. Sorry it's so long, but I hope it gives you a decent overview rather than being able to just, answer some questions. The next 2 lessons will be much shorter.